first exam, we covered everything about kinematics. Translational kinematics, rotational kinematics, and now we decided to add forces, and now it's called dynamics, right? So we apply force on some object. As a result, it starts moving. Dynamics, and we want to predict where the system is going to be under the influence of this or that force. And in terms of review, it's probably the easiest to review in terms of formulas. So we introduced a bunch of forces. And what is the force? Force, it's a quantity which we introduce to describe interactions. Because quite often when I ask students, what is the force? Immediately the response sort of like a F equals ma. No. This is the fundamental law, fundamental formula, but it's not a definition of the force. So definition of the force, we observe in our lives that objects interact. How can we model it in our theory? We introduce these new quantity forces, right? And we identified several forces, and we've been using them for the last month. All right, so first force. Whenever there is a cord, rope, string attached to an object, so of course that cord, string, whatever, exerts force on the object. Right, of course, assuming that that cord is stretched under the tension, right? So in that case, we introduce force, which is tension, which is along the cord and away from the object all the time. Sometimes we use symbol F sub t, sometimes T. Okay, T is kind of easier to write than F sub t. Right. Okay, so then we introduce the normal force. Normal force, whenever there is a connection or interaction between an object and some surface, it doesn't have to be flat surface, it can be curved surface, it can be any surface of any shape. Whenever there is such thing, so that surface exerts force, which we called normal force, right? Of course, description of that force is reasonably complicated, so we just know from our everyday experience that there is a force. And all the time, that force is perpendicular to the surface. That's the major feature of that force. Perpendicular. That's why it is called normal force. If the surface is horizontal, force is straight up. If the surface is inclined, still perpendicular to the surface. If you have two surfaces and the box is in contact with those surfaces, then of course there will be two normal forces. This way from that surface, and from this surface there will be force straight up. If person, let's say, tall enough and can reach the ceiling, and let's say pressing on the ceiling, of course that ceiling as a surface, of course is going to exert force also. Normal force, and it's perpendicular, right, to the surface, so in this case it's straight down. Okay, so that was the second force. Then we introduced friction force. Friction force is a little bit more complicated, and we subdivided this force into two: static friction and kinetic friction. Static, just from the name we know, it's a case when it appears when there is no sliding of the object on the surface, right? For example, this object box is on the inclined plane. Of course, gravitational force tries to drive it down, but because of the static friction force, this object is at rest, right? So velocity is 0, and static friction force in this up the inclined plane direction. Why that direction? Usually I recommend running this test, how to find the direction of the static friction force. Imagine what if static friction force disappears? Virtual motion will be, of course, down the incline. That's virtual, not a real motion. And the static friction force is in the direction opposite to the direction of that virtual motion. All right, and of course, all the time, let's say, for example, in this case, a horizontal surface, the box, and if you apply force, some applied force, of course, static friction force in the opposite direction, and in magnitude, this force and that force all the time the same. That's why there is no motion, right? There is no motion. Velocity is 0. And in general, static friction force is less or equal than this maximum possible static friction force. This is the experimental expression for the maximum possible static friction force, which can be found by multiplying coefficient of static friction and the normal force acting on the box. We've played with this force many times. Should be familiar. Then kinetic friction, when there is a sliding, actual motion. Here, it's sort of we were imagining virtual motions in order to find a direction of the force, and here actual motion, real. So if there's a sliding this way, kinetic friction force all the time is in the opposite direction. Right? And experimental expression for that force It's some kind of coefficient which we measure experimentally. We call kinetic friction coefficient times the value of the normal force, right? Okay, and then I like this graph because it's a very useful quite often, where we plot applied forces, this applied force, versus friction force, whatever friction force is acting in on the system. So first, in the case of static, when there is no motion, if you apply 1 Newton, static friction force will be able to throw back exactly the same force, keeping the object stationary. So you apply 1 Newton, static friction force will be 1 Newton. You apply 2 Newtons, static friction force will be also 2 Newtons. That's why this graph is at 45 degrees, right? But it cannot continue like this forever. Of course, at some point, if you apply strong enough force, the static friction force is ready to give up, right, and start sliding. So, and that is the maximum expression for the maximum possible static friction force. Okay, once you exceed this value, friction force drops in value, in the magnitude. Now it starts sliding, and the value of the kinetic friction force is smaller than the value of the maximum possible static friction force. And then this kinetic friction force stays the same in value all the time. Okay, of course, within experimental error. Then we introduce also gravitational force, ubiquitous. You all know that. I've never seen a student who wouldn't know this. mg straight down. Be careful, because sometimes students making silly mistake, thinking that it's something complicated, start imagining something strange. No, straight down all the time. Great. So these are forces which we've been using, right, in our problems. Now, fundamental laws which control this mechanical world. And they're all named after Newton. Newton's first law. Do you remember what's the role of the Newton's first law? Yeah, it allows us to find inertial reference frame, essentially reference frame which do not accelerate. And then as a result, not as a result, and then this Newton's second law, we all know, we discussed it, can be applied only if you try to solve the problem in that inertial reference frame. So Newton's first law is a tool which we use to find those inertial reference frames, right? Then, of course, Newton's second law. Once you're in that inertial reference frame, it's legitimate to use this Newton's second law. So if you have an object of mass m, you apply forces. Of course, it leads to the acceleration. And Newton noticed that these two quantities are related, right? So some of the forces acting on the object m leads to the acceleration of that object a, right? So again, it's not just F equals ma, it's universal law. Timeless, you can apply it at any point of the universe, at any moment of time, by anyone, and it should work, of course, for classical systems, for classical mechanical systems. World of quantum mechanics is a completely different world. And then if you have a two-dimensional system, you apply this law in the x direction, and you apply that law in the y direction. It's a three-dimensional system, apply also in the z direction. Newton's third law, whenever you have two objects interacting, of course, they exert forces on each other. And in absolute value, those forces are equal to each other, in absolute value. So if object 1 exerts force on the object 2, F21, at the same time, object 2 exerts force on object 1, F12, and these two forces the same in magnitude, and of course, opposite in their directions. As a result, we can write it in the vector form. Action, reaction, law, whatever it's called. Great. So, and then, of course, we can apply that for translational dynamics. It's very straightforward. Slightly more difficult to apply for rotational dynamics, so that's why I sort of prepared a picture. So if you have now rotational motion, of course, we can describe it using angular velocity or tangential velocity. Right? Then, if we assume that this motion is uniform circular motion, it means that the value of this velocity is constant. Right? In that case, tangential acceleration is 0, but we still have the second acceleration, centripetal, which basically describes how fast direction of this velocity changes in time. And that direction changes in time non-stop all the time. So that's the role of this acceleration. It describes how fast direction of the velocity changes in time. So since there is a circular motion, there must be centripetal acceleration. Whenever there is a centripetal acceleration, there must be circular motion, period, right? So then, which coordinate system is better to use to describe this motion? Again, we discussed. Since most of the vectors are either in the tangential direction or radial, it makes sense to pick those directions and align our axis along those directions. Tangential direction, radial direction. Radial direction is towards the center to make this centripetal acceleration positive, right? Okay, expression for the centripetal acceleration. We did not derive it in the class. I don't feel like it's needed, but most of the time we usually remember that v squared over r, tangential square of the tangential velocity divided by the radius of the circle trajectory. And so now, whenever there is an acceleration, of course, we all know there must be a force. In this case, that force is usually called centripetal force. But again, I keep telling you, I already told you a gazillion number of times, and I will keep telling you that there is no such thing as a centripetal force as a new kind of force. No, our normal regular forces which we introduced over here, they play the role of the centripetal force. Sometimes it can be, I know, tension plays the role of the centripetal force. Like if I take this marker and start spinning it, so in this case, tension plays the role of the centripetal force. Sometimes normal force can play that role. Sometimes a friction force, like a car when it goes over a circular road, plays that role. Sometimes it's a superposition of several forces. It's sort of like, as I said, let's say there's a famous role of Hamlet, that play, right, written by Shakespeare. So there's a role of Hamlet, and different actors, depending on the theater, depending on the country, plays that role, right? So the same here. There is a role, centripetal force, and different forces play that role, right? And so then, if we want to describe dynamics of the system, of course, we need to apply universal law, Newton's second law, in the radial direction. Right? Sum of the forces in the radial direction equals to mass times the centripetal acceleration, right? Okay, so that's essentially the scope of the material for this exam. Yeah, so about eight problems. Okay, the first one is somewhat similar to what we solved in our recitation class. But again, it's a review. Again, don't expect some fancy problem, something new. We're just reviewing. All right. So, inclined plane, there is a child sliding from the top. The angle of inclination is given. The length of the incline is also given. And we need to find the velocity at the bottom of that inclined plane. So, problem number one. And which way I inclined it, that way. Okay, good enough. So there is a child sliding. So the angle of inclination, as I said, is given. Theta equals to, okay, I need to grab my notes, 34 degrees. Then there's a child. You know what, yeah, I usually use the box, but I don't feel like using the box instead of a child. So let me draw something. Right. Okay, good. Two legs. Okay, and that is sliding down. So then it's okay. It was released. Okay, the initial velocity was 0. It was released. Sounds like the child was tortured, right? Then there is a friction. So it's not a frictionless surface. So there is a friction, mu k, 0.51. And the length of that inclined plane is 10 meters. Okay, plenty of information. Right, and we need to find, let me write down over here. So we need to find velocity, okay, at the bottom. something similar we solved, but it was like 3 weeks ago in our recitation classes. So let's just quickly review. Any problem of this type, the procedure is straightforward. Every time you need to repeat exactly the same steps. Introduce coordinate system. Identify all forces acting on the object, right? Sort of like mentally walk around the object, identifying all the interactions. Then, once you complete free body diagram, grab Newton's second law, universal law, which can be used to describe motion of any system, classical system. Literally, there are no limitations, but in the classical world. And then, once you apply it, you will get 1, 2, 3, or 4 equations, and then you'll start looking at those equations and making a decision what is given, what needs to be found. Essentially, at that point, you just need to solve a system of equation with some number of unknowns. So all the time, exactly the same steps. Okay, so let me start with the coordinate system. Again, coordinate system, it's up to you which one to pick. There is no right or wrong coordinate system. There are more convenient coordinate systems, there are less convenient coordinate systems. The most convenient in this case, it's when the x-axis along the incline, right? So let me show it. So this will be my x-axis. Okay, of course it goes all the way down. And y-axis perpendicular. And also I'm going to position the origin at the point where the child, again it doesn't sound like was released, where the child started sliding. Right. So this is the origin. And so coordinate system is here. Now forces. Gravitational force straight down. So far I didn't see any problems with that. Right. Occasionally I see students sort of they develop the habit of the force. Gravitational force is kind of perpendicular to the surface, and they draw it this way. No, guys, careful, right? So, but again, it doesn't happen that often. Occasionally, I see that. Then there is an interaction with the surface. There must be normal force perpendicular to the surface. So there must be normal force, Fn. Right. And then what else should act on the system? On the child. What else acts on the child? Friction force. Since there is a physical motion of this child, every time I want to say object, no. So since object slides down, okay, the child slides down. So the friction force must be up the incline. And this is the kinetic friction. Okay, essentially almost completed free body diagram. Right? And of course, at some point, okay, in a minute, we will start applying Newton's second law in both directions. And this force fully in the y direction, this force fully in the x direction, but mg is somewhere in between. So let's just decompose gravitational force quickly so that everything will be ready for Newton's second law. Okay, so of course, this will be our component of the gravitational force in the y direction. Then if you draw a normal line, this will be component of the force in the x direction. And now be careful with angles, because again, that's the place for mistakes where I think you shouldn't be making mistakes. So if this angle theta, then of course, what can you say about, for example, this angle? Look at this triangle, this point, that point. That angle will be 90 minus theta. Because this angle is 90 degrees, that is theta. Sum of angles of all angles in a triangle must be equal to 180 degrees. So this will be 90 minus theta. But we need to know this angle. And if this 90 minus theta, then this angle must be equal to theta. Because this angle and that angle, they add each other to 90 degrees. So that's what I usually do in order to convince myself that this angle equals to that angle. If I start doubting myself, for example. So now as a result, what's the expression for this y component of the force? MYG. Yeah, expression for that. Yeah, sine theta, mg times, oh, careful, Sine or what? Look, we're trying to find a side which is adjacent to the given angle, right? Yeah, cosine, of course, cosine. Again, guys, be careful, because it's a big issue, actually, for students with cosine and sine functions, even in physics 2 still, for some time. So mg times cosine theta. Great, so now this component, x component, of course, now it should be sine, right? Because essentially this component equals to this side equals to this side. So it will be, essentially we're finding side opposite to the given angle. So this is mg times sine theta. Okay, so now we're all set in order to start applying Newton's second law. So now, okay, let me start in general, in a vector form, Newton's second law, right? And now, first in the, I bugged my students, okay, my students, I mean in my recitation classes. Every time at this point, I start with the equation in the y direction. And there is a really reason. If I start with the y equation, I will be able to find normal force. All right? Once I know normal force, can I find the friction force? I will be able to find the friction force. And friction force is involved in the equation, in the x equation. Right? So if I start with the y equation, I prepare a friction force, and then I can use it immediately in the equation in the x direction, Newton's second law in the x direction. So it makes the solution, at least in my opinion, somewhat smoother. So that's why I usually start with the y equation. Sum of the forces in the y direction equals mass times acceleration in the y direction. What's the acceleration in the y direction? Zero, guys. Don't think applying g or something like that. The logic is simple, right? So we observe that this child doesn't move in the y direction, doesn't jump, doesn't do any movements in the y direction. So it means that acceleration is zero. At this point, we have to apply observation in order to continue solving the problem. Right? So we need to we need to apply what we observe in the situation. So 0, and I will write observation. Right? Since there is no motion in the y direction. So as a result, I can write explicitly normal force is positive. This component of the gravitational force negative. Again, positive or negative relative to the chosen y direction. That's why I demand, if you don't show coordinate system in the problem, immediately I don't know I wouldn't know how to grade. I wouldn't be able to tell if this sign positive, correct or wrong. Of course, I can deduce if everything is correct. I should be able to deduce your coordinate system. But as a grader, I shouldn't be doing that. Every time you should explain everything. Like when you start writing papers, the reviewers will demand from you the full range of explanations. So mg times cosine theta equals to 0. Of course, from here we'll get normal force. Mg cosine theta, of course, we've done it many times. And now, as a result, immediately I should be able to find expression for the kinetic friction. So F kinetic equals to mu k is given, yeah, times normal force, mu k mg times cosine theta. Okay, let me frame it lightly, because soon I will need it. Okay, so that's basically, the outcome from the equation in the y direction. So now the equation in the x direction, sum of the forces in the x direction, mass times acceleration. I dropped the subscript because essentially we have only one acceleration in the system, so I don't want to drag that a sub x. And so now forces. Gravitational component of the gravitational force in the x direction. Positive, because again, you see it points in the positive x direction. So it must go into the equation with plus. So mg sine theta minus kinetic friction equals to mass times acceleration. Right. Okay, so now this kinetic friction can be plugged, and we will get almost final expression for the acceleration. So it will be mg sine theta minus mu k mg cosine theta equals mass times acceleration. Right. What can be done with mass? We can do that mass destruction, right? Cancellation. So m goes. And as a result, we're getting expression for the acceleration. So acceleration equals to, I will factor out g because it's the same for both terms. G sine theta minus mu k cosine theta. That's it? Yeah, nothing else. Okay, so that's the acceleration. But again, it's not the final result. It's acceleration. Numbers are given. You can plug them. If you plug them, you will get 1.37 meters per square seconds. What's the direction of acceleration? Is it accelerating or decelerating? Since your answer is positive, it means that acceleration as a vector in the positive x direction. So it means the object, a child, accelerates. If you get minus, for example, on the exam, for whatever reason it's possible, don't try to hide it, don't panic. It means that, okay, that minus has a meaning. Minus would mean that acceleration is up the incline in the negative x direction. It means that, yeah, object is still sliding down, but decelerating, moving slower and slower and slower. If you get minus, don't panic, because I see quite often students, oh, maybe I've done something wrong, let me hide it somewhere. I usually see it, and anyone will see it. Okay, so now what's next? So we found acceleration, but the question is about velocity. So I usually give this diagram. So what we've done so just now, you remember in the exam 1, we were in the world of kinematics. We described, okay, we learned how to describe motion. And in the world of kinematics, we had what? Position, velocity, acceleration, time. It's a world of kinematics. Now we added forces, the world of forces, right? So let's say over here, we added the world of forces. And now, using this Newton's second law allowed us to move from the world of forces to the world of kinematics to the level of acceleration. Right? So here, using Newton's second law, ma, right? So now we are in the world of kinematics on the level of acceleration. And now, if acceleration is constant, we can use our kinematic equations. We can find velocity, like in our case. We can find position. We can find travel time. We can find whatever we need to find once you are in that world. So right now, we made this transition from here to there. Now we are at that level. Right? And we need to find this. This is our unknown, right? So we need to find this velocity. So now, of course, is it legitimate to use kinematic equations? Why? You're nodding. Okay. What? Say it again. What you're saying is absolutely correct. You already essentially started applying kinematic equations. But before we start applying them, we need to justify, is it legal to use them in the first place? Is it legal? Why? No. Again, you're trying to apply it. But before that, we need to pronounce keyword. Okay, pronounce it. That you justify why we use Newton's second law. So yeah, we used some observer which is standing over here, stationary, right, inertial reference frame, and it's illegal to use Newton's second law. Acceleration is constant. Every time I will keep bugging you about that, because sometimes acceleration is not constant in that kinematic, and then kinematic equations cannot be used. In that case, you will have to integrate second-order differential equation. That's what Newton's second law essentially is. Right? So since acceleration is constant, yeah, it's illegal to use kinematic equations. So let me write that down. Since acceleration is constant, okay, that's my constant, because sometimes students are confused. What is that? C-O-N-S-T, S-T. Right. Kinematic equations can be used. Okay, and now what you were telling, now we can continue it with your words. Yeah, now which equation is the best? We have three. Equation to predict the future of this velocity, future of the position, and then no time equation. And of course, which equation will be the best? Yeah, of course, you saw that number 3. Since the question is not about finding time, information about time is not given. So usually, most likely equation number 3 will be the most convenient. Right? So let's use that no time equation. So v squared, in this case it's a final, equals to v initial squared plus 2a x final minus x initial. Okay, equation number 3. Let's immediately simplify it. Initial velocity is 0. The child started with 0 velocity. Then initial coordinate x equals 0. 0 because that's where I position the origin. I position the origin at the point where the child started sliding. So this is also 0. This is given, it's a 10 meters. Right? So this is L. And that's it. Right? So we need to find this. So from here, v final equals to square root of 2a times L. Okay, numbers. We have, if you plug them, I will look at my notes. 5.24 meters per second. Okay, it's quite a speed. To have some fun. Again, essentially, the problem consists of many steps, but ideological. First, you apply Newton's second law to find acceleration, and then one of the kinematic equations. But of course, in order to have the whole picture, of course, you need to complete free body diagram. And almost for every problem, because every problem will be about Newton's second law, it will be first part. Draw a free body diagram. If you don't do that, it's a beginning, essential part of the Newtonian formalism. You need to complete free body diagram because all the equations are written based on the diagram. It's supposed to help you. Yeah. Yeah, they're given in the formula sheet. Again, look at the blackboard, the previous year exam. Right. Okay, I will post also the formula sheet of this year, but essentially it will be essentially the same. Right. Of course, yeah, all these formulas will be given. All right. Okay, anything else? Yeah. Me personally, I prefer to draw all this diagram actually on a physical diagram. Some students usually draw, not usually, sometimes they put a dot somewhere outside and then draw all the forces outside of the physical diagram. Again, if you prefer to do it that way, okay, do it. For me, I prefer to draw all the forces on the picture. Of course, I usually also try to add pictures to the problem, so use it if you want. Of course, that was my logic. Great. So problem number 1. Okay, now the second one. So the idea is this. Okay, then I will start erasing it. So there is a wall. So there is some box. Okay, I don't have any other boxes but my bottle. And we apply some force at a certain angle. So we need to calculate how much of force must be applied so that this box would slide down without acceleration, with constant speed. Right? So there will be some information given, but essentially this is the physical, this is the idea of the problem. Can I start erasing it? So number 2. So we have a box against the wall. So we have a box Okay, I will first draw the picture and then I will write down what is given. Actually, not much is given. So first the wall. Then the box. Mass is given. 2 kilograms. 2 sig figs are given. Then there is an external force applied. I know. You apply it with your hand, with your finger. And that force is what? At 45 degrees. So this is the force F. And as I said just now, this angle is 45 degrees. Okay, in terms of numbers, I think that's it. Nothing else. No, coefficient of kinetic friction is given. Mu k. Wait, that's an ugly k. Equals to what? 0.2. Since the object is going to experience sliding, so this is kinetic friction. Kinetic friction coefficient. Yeah. So what we need to find? So we need to find the value of that force. So that velocity, why I paused, because right now I want to write velocity in the y direction is 0, but I haven't introduced coordinate system yet. Okay, let me immediately introduce coordinate system and then we'll continue. I'm going to align it like this. Y direction, y coordinate is going to be upward. Although I cannot justify why not downward. It's going to move in the object is going to slide this way. I don't know, I just picked it. I cannot justify that this is better than downward. So both y upward or downward, they're equally good. And of course, x-axis will be horizontal. X. Okay, and so now v sub y, it means that velocity in this direction, constant. So no acceleration, without acceleration. So that's it. I think that's what is given. And actually, at this point, I even don't care what needs to be found. Usually, I start thinking of what needs to be found much, much later. Because before, we need to complete free body diagram, identify all the forces, introduce coordinate system, and then I start applying Newton's second law, and only then I will start actually looking. What do I have to find? Where is my unknown? What is given in my equations? But up to that point, I actually don't care what needs to be found. Right. So, free body diagram, and start applying Newton's second law. All the time, we're going to follow that recipe. So, forces. Now I will bug you. The first force, except for this one. what acts on the box. Again, forces on the box. Of course, there are forces acting on the wall. We don't need those forces, right? Because we want to apply Newton's second law for the box. So this, so all the forces acting on the box only. Not, we don't need forces acting on the wall. So the first force, any acting on the box. Of course, usually students immediately go with the gravity, right? It's a safe bet, right? So the Earth is down below, so gravitational force is straight down, right? So I will probably draw it from the center of mass, from the center. Right, so somewhere here. So gravitational force, mg. Then second force. Wow, I thought you would go with another force. Friction force, yes. What's the direction of the friction force? Straight up. Because we assume that, okay, not assume, we want for the box to slide down. So velocity will be downward. So, of course, kinetic friction force is in the direction opposite to that direction. So let me show you with the blue. So this is the direction of the velocity, v. Right? So as a result, you see I use different color because I usually use red only for the forces. And acceleration, because those are essential players. And this we need in order to sort of determine the direction of the friction force. So since velocity down, friction force must be up. Wait, not straight one, kinetic. Right. And the last force. Normal force, right? Yeah, normal force this way. So let me draw it, Fn. Again, guys, of course, the box is going to apply force on the wall, but we don't need that force. We only need forces acting on the box, right? If we were interested in the life of the wall, yeah, we would have to include that force, but we don't care about the life of the wall. Right? The wall is an external object which exerts force, which is a normal force, right? That's it. So here there is a wall, normal force. Earth over here, gravitational force. Here is the finger or the hand of a person. And of course, friction force because there is a roughness of the surface. That's it. So nothing else. And so at this point, we're ready to start applying Newton's second law. But before we do that, we need to do first what? Before I start applying Newton's second law. Preliminary step. I would decompose it, right? Let's just quickly decompose this force in the x direction and the y direction, and after that, everything will be ready to start using Newton's second law. So dash line. So this is the x component of this force, applied force. You see? And this will be the y component. Okay, I will draw it maybe over here. Right. Or you can draw it over here as well. Which way I wrote in terms of, okay, still in terms of angle. So theta. Theta equals 45 degrees. So horizontal force. Cosine or sine, in order to find horizontal force. Cosine, yes. So this is angle theta also. This and that angle are the same. Right, so of course cosine. So F times cosine of angle. And if that was, if in order to find that we use cosine, of course, in order to find this component, there will be sine. Because this side is opposite to the given angle. So this will be F sine theta. Okay, that's it. So everything now is in front of our eyes. So we just need to transport it into our equations with the proper signs. Okay, so Newton's second law. First, I will write it in a vector form, and now we just need to apply it in both of these directions. Probably again, I will start with the y direction. Let me do it. So first, No, not y. Okay, sorry guys, let me change my mind. I want to do x, and I think that's what you wanted to tell me, yeah. Let me do first x direction. You understand why? Because now normal force in the x direction, I want to find first that normal force because I will need that to find the friction force. Right. Okay? And now we need to write explicitly. Normal force, positive, negative, positive, because it acts in the positive x direction. So you see again, plus Fn. Then, component of this force, applied force. Component of the applied force, positive, negative. This force, F cosine theta, because you see it is in the x direction. Is it positive or negative? Yeah, negative. It points in the negative x direction, so it must go into the equation with minus. So minus F cosine theta. Anything else? No, that's it. That's it, right? Equals to 0. So normal force equals to, wait. Muscle memory. Usually mg cosine theta, but in this case it's F cosine theta, right? F cosine theta. And again, before I start writing down equation in the y direction, I can find the kinetic friction force, right? Kinetic friction force, because we need it for that equation. Right? So now we can get F kinetic equals to kinetic friction coefficient times the value of the normal force. Okay, guys, if something is not clear of this or that step, tell me immediately. Again, it's our time, our free time, so we can spend as much time as we want, right? So we can, yeah. Okay. This? Yeah. Ooh, Why didn't tell me immediately, right? Okay, I set velocity constant. It actually showed on the, no, constant. Acceleration is 0 without 0. Acceleration is 0. Velocity is constant. Wow. Sorry, guys. Yeah. Yeah, this is basically, no, with the finger, right? Somebody's pressing. So, and is applied at 45 degrees. Essentially, the question is, we just need to calculate how much force do we have to apply so that the box would slide down without acceleration. I know the piano is slowly dragging down, right? Yeah, okay, so this is a sometimes it happens. Guys from my recitation classes know. All right, so this, we can plug it over here, and we can get mu k F times cosine theta. Right. Okay, so now we can leave it for now. Okay, I will frame it because, again, I will need it in a second. So we exhausted this equation. Now we need to do the same in the y direction. So I will put a new bullet. And sum of the forces in the y direction equals to mass times acceleration in the y direction. Over here, I should have actually also written this acceleration is 0 y, because we observe. So there's no motion of the box in this x direction. So acceleration equals 0. Again, just observation. We applied observation. No motion in x direction. And so now, what about this acceleration? Which I confused, right? Set constant velocity, rho 0. this acceleration is 0 because we want. That's what we want. We want a velocity constant. It means acceleration is 0. And now I will write we want. That's what we want. Okay, and now let's just write down explicitly this equation. Y. Okay, Fk positive. You see, it points in the positive y direction. Then this gravitational force negative, right? Gravitational force. And this force positive or negative? Positive. Again, guys, be careful because sometimes there will be problems with, I know, 3, 4, maybe 5 forces. Make sure that you include all the components of all those forces, right? So carefully look at the diagram. Don't rush. So Fk positive, then mg negative, and this force is positive, plus F sine theta. Again, let me check to make sure that I include all forces. Yeah, that's it. And equals to 0. So now let me get this kinetic friction, which we prepared. Now we can use it over here. So we will get mu k F cosine theta. Essentially, I'm just rewriting this equation with this expression for the kinetic friction force. Then minus mg plus F sine theta equals to 0. And essentially, only now I start thinking, my brain started thinking, so what do we actually need to find now? Because we have all the equations that we can extract in front of us, and now I start thinking what needs to be found. We need to find the force. Force is over here, right? And of course here as well. So our unknown here and here. Then this is given, angle is given, mass given, g of course given, angle is given. Okay, so one equation, one unknown. Essentially we solved the problem. So we just need to write explicitly F in terms of the rest of the parameters, right? So you see, one equation with one unknown. So essentially we almost solved it. So let me move this acceleration, that force to that side with plus and factor out F. So F sine theta plus mu k cosine theta equals to mass times acceleration. So I just rewrote it. Preparation. And so now F will be equal to, am I right? Yeah. So F equals to mg divided by this construction. So numbers are given. So if you plug, you will get 23 newtons. Of course, don't forget about units. And not just at the very end. If you found some preliminary results, values if you calculated, so write down the unit. And again, I just keep telling you, follow the procedure. Draw a diagram and then start applying. Yeah, you can make some mistakes here and there, but if your solution will be structured, you will get plenty of points, right? Because that's essentially what you need to learn, some fundamental laws and then the procedures. And the same in advanced level classical mechanics courses, the same idea. You first present some set of fundamental laws, axioms, and then you just learn the procedures, how to apply that. Mm-hmm. Oh, no. Of course, numerically they're equal, but I can easily change to 30 degrees or 60 degrees, and of course they will not be equal, right? So I would never recommend swapping, right? So no. Actually, in that case, yeah, you can claim that you use a different angle, right? So not that 45, but the complementary 45, right? So in that case, it will be difficult to argue with your, yeah, you can do it. Yeah, in that case, I wouldn't be able to object. Okay, anything else? Okay. Now, next one. Let's just discuss elevators. Classical problem offered almost every exam. Yeah. Huh? Yeah, of course, yeah. That's why I usually ask is, can I start erasing it? So the elevator, there will be accelerating, upward, downward, no acceleration. So let's just quickly discuss all possible situations and also all possible directions of the coordinate system. Y-axis, upward or downward. Okay, for now I will change the number of the problem. Number 3, and now it will be elevator. Done? Yeah, okay, great. So now let me erase it. And essentially the questions are about apparent weight. You remember what apparent weight is? It's about feelings, our feelings in the elevator. Physics doesn't often talk about feelings, but in this case we're talking about what we feel. Right? And even special term was introduced, apparent weight. Again, let me just quickly remind you. So weight in general, by definition, it's our mass times acceleration due to gravity. So that doesn't change unless you change the Earth to something else, right? So weight mg is exactly the same. But what we feel, it depends. If I'm standing right now on the solid floor, which doesn't accelerate, of course, a normal force, that's what we feel with our feet, right? So we don't feel our weight directly. We only feel the normal force. So in this case, since there's no acceleration, so my weight mg equals to the normal force, and we feel our normal weight, right? But of course, not directly, indirectly. But if I step in the elevator and press the button, of course, now the floor will be accelerating upward or downward. And of course, depending on the direction of acceleration, we can feel heavier or we feel lighter, right? But again, it's only feeling. Our weight will be still the same. Or if somebody cut the cord of the elevator, then of course you will feel nothing, right? Of course, except for terrifying. So now let's discuss several cases. So the first one, let me draw the elevator. Right, so the cord. The first case, let's assume, let me draw the person first. Right. And let's assume it moves up velocity. And let's assume that acceleration is also upward. It's accelerating up. And so again, we need to answer the question, what does this person feel? Heavier, lighter, or just a normal weight? Right. The same procedure, free body diagram, coordinate system, and apply Newton's second law. Everything must come from the Newton's second law. It's a universal law, global law, right? Okay. Forces. only forces acting on the person, because again, based on the quiz number 2, where we ask you to draw forces, we realize, actually I knew that, and that's why I created that quiz, to force you to sort of, I don't know, realize and remember. Whenever you apply Newton's second law, you need to only include forces acting on this M. Because there are tons of forces around this elevator, but we need to apply only forces which act on the person, not on the elevator. Right? So forces acting on the person, of course, ubiquitous gravitational force straight down. Right? So mg. And then, of course, normal force from the floor. Fn. Because in the quiz, plenty of students, they also included this tension force. Why don't we need a tension force in this problem? Exactly. It's not acting on the person. It acts on the elevator. And the elevator acts on the person through this normal force. So the effect of that tension force on the person will be sort of delivered to the person through this normal force. Right? So we only need forces which directly act on the person. Right? Of course, there will be also a weight acting on the elevator, but again, that's the force acting on the elevator. We don't need that force. So only two forces, normal force and force of gravity. And the last piece which I need to include in my diagram, you do know, everyone knows. Which direction, for example, positive? Which direction is negative? How can I tell you? How can it? Coordinate system must be included, right? So we need to include coordinate system in order to tell the reader, the person who is going, or even to yourself when you're going to solve, which direction is positive, which direction is negative. So we need to include coordinate system. Upward, downward, it doesn't matter. But first, let me use this, y-axis upward. Why did I pick y upward? Can you? Acceleration. I don't want to have my acceleration to be negative. Again, there's nothing wrong with being negative, but I don't like minuses, and I'm sure that you have the same sentiment. Right? So now, free body diagram is complete, and of course we can write down Newton's second law. So sum of all forces in the y direction equals mass times acceleration. And again, mass, it's a guy. Okay, the person. Acceleration in the y direction, right? Okay, so now let's apply explicitly normal force positive, gravitational force. Yeah. What is given? We can say acceleration is given. Okay, let me write down what is given. Acceleration. We can say mass. What else do we need? Acceleration due to gravity. Right. I will add if I forget something. Right. Okay, so normal force is positive, gravitational force is negative, mass times, and acceleration is given ma, and it's positive. Again, where is the feeling of the person in the elevator? Apparent weight. It's a normal force. Again, you see the person doesn't feel directly weight. It feels normal force, reaction from the floor. Right. So even, let me write it down. So this is apparent weight. Right. Okay, so let's solve it for that Fn. It will be equal to mg plus ma. So heavier or lighter? What does he feel? She feels. Yeah, of course, heavier. So this is the weight, actual weight. And now plus some term which is not negative, which is positive. So we're adding some positive number to our weight, right? So the larger acceleration, the heavier you feel, right? And so which way I wrote it? I just circle it. So So this is our weight, and plus some additional contribution because of the acceleration. So it feels heavy. Okay, not okay. It feels heavier. Let me just write this. Feels heavier. Right? Even questions like this can be, I know, among multiple choice questions because it takes, I know, a couple of minutes maximum, even less than that, in order to come to the conclusion. So now let me just quickly, what if y-axis is downward? Okay, not up, but down. So the same problem, but what if I change coordinate system? So what happens to this equation? A normal force now would be, relative to this direction, will be what? Negative. mg will be positive. So it will be now then. So it will be mg minus fn equals to mass. And what about acceleration? Acceleration is negative. Acceleration is negative because acceleration is given, acceleration is up, and relative to this direction, it would be negative. So if you don't include that minus, of course, you will get some bizarre result. And that's why we usually choose the coordinate system, y-axis, in the direction of acceleration. Because usually students develop a strong habit of writing proper, correct signs next to the forces, but they don't very often pay attention to the acceleration. As a result, chances that you're going to make mistake will go up significantly. And so now let's just solve it for fn. So it will go to that side. This term will go to this side. Of course, signs will be changed. So it will be fn equals to mg plus ma. So the same result. So coordinate system should not, of course, must not affect the result. So the same. Wait, this, yeah, the same. As it should be, or even as it must be, as it must be. So now let's look at the second situation. Okay, clear? Again, it's not rocket science. After a couple of examples, it should be straightforward. And plus, you see, we're repeating exactly the same steps over and over again, but you need to apply them very carefully, right? So now let's assume that acceleration is downward. So new elevator. So again, the court, the person, right? And now velocity is still up, but now let's assume acceleration is down. And the same, what about that person's feelings? Forces, the same, mg, normal force. And now if I ask you, what must be included next? Of coordinate system, right? So of course, which one I picked? And of course, you can easily guess coordinate system. The most convenient will be downward. Again, it's convenient. It doesn't mean that it's the only one which is correct. In order to make acceleration positive. So y downward. And so now the same. Newton's second law, universal law. So mg positive, normal force negative. Mg minus Fn equals to mass times acceleration. Again, the feelings are in the normal force. That's what we feel. That's what I'm standing right now and feel like my feet is getting hurt by the end of the day. Right. Normal force equals to, okay, it goes to that side. This term goes to this side with minus, of course. This goes to that side with plus. This goes to this side with minus. Again, careful with the pluses and minuses. So it will be mg minus ma. Here we had mg plus ma. Ma is the positive number, right? So, but now we have minus. So it means that the person is going to feel lighter. Right? And of course, again, as I said, if you cut the cord of the elevator, then what will be this acceleration? What will be the value of that acceleration? G. So you're going to have mg minus mg. 0. Normal force disappears, so you're flying, right? Basically with the elevator together, right? So again, it doesn't mean that your weight disappears. No, your weight will be still there. You would still feel this. You would still have the same weight, but you're not going to feel it because there is no response from the floor, because the floor is flying next with you with the same velocity, with the same acceleration. But right now it just feels lighter. The person would feel lighter. So feels lighter. Right. Because of this minus then next example, which quite often students, where quite often students making really, really silly mistakes because they don't read problem carefully. Because they usually think about this case or that case. What if we have this situation now? Right, so again, the elevator, right, so the person, right, and now it moves up, velocity. And usually the problem says, let's assume that elevator moves with a constant speed upward. Describe the feeling of the person, okay, in terms of apparent weight. And students go into this manipulation with acceleration and all so on and so forth, right? Jump into the conclusion the person feels heavier or lighter. But what's the answer? Velocity is constant, acceleration is 0. So the person would feel it's her normal weight. Normal force will be equal to the gravitational force. Essentially, there is no difference between me standing on the stationary floor or me standing in the elevator, which moves without acceleration. Right? And of course, we all experience that in tall buildings when it reaches cruising speed. Of course, you don't feel anything. So it means that in this case, I can show that it means that acceleration equals 0. And in this case, discussion is much, much easier. Right? So be careful. If velocity, we need to know information about acceleration. If acceleration is 0, then of course it's easier. So and acceleration is 0. So in this case, yeah, I can still draw the same forces. Normal force, force of gravity. I can introduce coordinate system to be precise. Coordinate system, it doesn't matter which direction, upward or downward. There's no acceleration, right? So I picked up. And as a result, we're going to get normal force, positive minus mg equals to 0. You see, everything comes from Newton's second law. It's one of those fundamental laws. Like in physics 2, electricity and magnetism, you're going to introduce Gauss's law, Ampere's law, Faraday's law, basically which are fundamental laws. This is something similar. Okay. Okay, let me write feels normal. Feels normal. Okay, let me check my. Why it's not recording? Ah, I think I didn't start it. Okay, I don't remember if it was running or not. Okay, anyway, I still have a front camera footage. Yeah, it's recording. Okay, any questions? Yeah, it shouldn't be complicated now. Let me switch to the next problem, number 4. Okay, so now motion of objects, two objects connected somehow. You remember those type of problems? We solved several. So now, okay, motion of connected objects. Motion of connected objects. You know what? I think I need to change. And so it's easier to start drawing than to explain. So inclined plane and then vertical plane. The angle is given. Then over here there is a pulley. You remember we solved problems of this type. So pulley, massless and frictionless. And then there are two boxes. The first one is here. The second one will be here. Right. So which way I label them? This is M1. This is M2. So what else is given? Masses, angle. And another thing is given. Again, finger will be involved over here. We're going to apply force on the second box, the first box, horizontally. So the whole system, you feel, is going to slide like this, right? So we're going to apply also additional force that way to make the problem more complicated. All right, so now I'm going to apply force F, right? So now what is given? M1, M2, then angle is given, and force, which is horizontal. And this surface is rough, so there is a friction. And also mu sub k. Yeah, that's it. And you can guess what needs to be found easily, probably. What's the acceleration of the whole system? And also, what's the tension in this cord? So let me write. So let's find acceleration and the, okay. Did I use T capital? Okay, let me use T capital. Just, it's much easier to write T capital than F sub T capital. Right? Yeah, that's it. State is given. Yeah, I wrote it down. Looks complicated, but there's no reason to panic because, again, we know the recipe. You just need to introduce coordinate system. Now we have two objects, and it's still legitimate to introduce coordinate system for each object separately. So one for this, one for that. And then, again, identify all the forces acting on this object, on that object, and apply Newton's second law then for that and this. So just increase number of equations in your system. But ideology of the problem is exactly the same, just you'll have more equations and more terms. So you need to juggle more things, larger number of elements at the same time. And again, for now, it sounds like, wow, complicated. Slowly start moving without panicking. Coordinate system, again, the most convenient, x-axis up the incline or down the incline. It doesn't really matter in this case. And y-axis is perpendicular. Again, it's the most convenient, not the only one which is correct. So x and y. That's for this M1. For M2, obviously, it's only one directional motion. So we assume that this mass is not swinging in any direction. So it only moves up and down. That can be easily achieved. So since most likely the system is going to accelerate this way, I'm going to align my y-axis that way, downward. Yeah? Yeah. So y. Again, if you pick it upward, again, it's not a big deal. But of course, in that case, you will have to write equations properly. And acceleration most likely would be negative in your for this object. Okay, so coordinate system here, and now let's start identifying all forces. One force is given, right? And now this gravitational force, everyone knows. So far, I don't want to ask you because I notice everyone can easily find that force. Then normal force perpendicular, as we already did many times today. Normal force. And then what next? Yeah, tension. There's a rope. There's a rope, so there must be tension. Again, along the rope, away. What? I can do better than this. Which way I label it? FT or T? Okay, I will. Yeah, already labeled T. Okay, T capital. And what else? Friction force. Friction force, yeah. Since we assume object, is it given or not? Okay, so we assume that object moves this way, right? So the friction force will be, of course, in the opposite direction. Right, so, you know what? Let me make it slightly longer, this force. F kinetic. Because, no, it's still possible. Velocity. Okay, let's assume that velocity that way. Accelerating or decelerating, but anyway, let's assume the whole system is moving this way, sort of counterclockwise. Pulley is massless and frictionless, so it doesn't contribute anything. Pulleys, when the pulleys are going to be not massless, we will discuss maybe in a month or so. And also, we assume that cord is massless. So in that case, tension over here, tension at any part of the cord must be exactly the same. Right? We discussed that in the lecture. That's it. So tons of forces, right? Just we'll have more terms, but ideology is still the same. Now let's discuss forces acting on this object. Gravitational force. Okay, there is one Not a mistake. Of course, sooner or later I will notice it. What is missing in my diagram? Yes, yes, exactly, right. So because now I started thinking about this, that's why I stopped M2, and then I realized that over here M1 is not written. So M1. Yeah, we need to differentiate them. M1. So this is M2G. Usually in a few minutes you will spot it if you do it carefully. And tension, tension is exactly the same, so we don't have to differentiate those guys because the cord is massless. Okay, that's it. So free body diagram, but again, before I start applying usually Newton's second law, I prefer to decompose all forces. Right? Nothing to do here, or kinetic friction, but this force and that force we need to decompose into the x and y components. Right? So let's do that. So this, you know what, I will use probably different color. So horizontal component, where should I, okay, I will draw it here. What can you say about this angle? This angle and that angle are exactly the same. Why? Because this, you see the bottom of this inclined plane, it's horizontal. Also, the line of the force, also horizontal. And so, as a result, this angle and that angle are exactly the same. Right? So, this is theta also. Right. Okay, so now, once we know that angle, we can find this component. So, it will be F times component component which is adjusting to the angle, given angle, right? So it's a F times cosine of theta. F cosine of theta. Okay, so now the perpendicular to the motion, where should I draw it? Okay, let me draw it here. So that's this way, right? And that component is, of course, will be, this is angle theta, so that component is F sine theta. Okay, now let's also decompose quickly gravitational force. It's much easier because we've done it already several times today. All right, so this will be our y component, and this will be our x component. So these are angle theta. So it's mg times cosine theta. And that component, okay, let me draw it like this. Mg sine. Lots of components, lots of forces, so carefully. Okay, so now everything is in front of our eyes, and now let's start applying. And I will start again with the equation in the y direction for this object. So first object, I want to discuss object M1. And then later on only object M2. So M1 in the y direction, so sum of the forces on the first object in the y direction equals to M1 acceleration of the first object in the y direction. There is no motion in the y direction of the first object, so acceleration is 0. Right. No motion. And so we can write it. So normal force, positive. Then, what else? This one of these green forces, this one, F sine, negative. Yeah, you see, y direction is that way, but this component is in the opposite direction. So this component is negative. So it's a minus F sine, F sine theta. Then component of the gravitational force also negative. So it's mg cosine minus. Right. And I think that's it, right? That's that, yeah. Yeah. Equals to 0. We solved similar problem in the recitation class, but this force F was missing. So essentially, in all the equations, just additional term will be added. Otherwise, problems is very, very similar. So I will have to find friction force, kinetic friction force for the equation in the x direction. So let me solve this for the normal force in order to find kinetic friction force. Right? So let me solve it for Fn. So both terms goes to that side. So it's a mg cosine theta plus F sine theta, and from here I can get the kinetic friction. This is normal force, this is kinetic friction force, right? So subscripts are different. So it's a mu k times normal force. So just all this will be moved over there. Mu k. Can I factor out something? No, nothing can be factored out. Cosine theta plus F sine theta. Okay, so that's kinetic friction force. It's not the final result, but I will need it in a few minutes. So we exhausted equation in the y direction. So now let's do the same, but in the x direction. But again, still about mass m1. We're still playing with this mass. So we apply equation in this direction, now in this direction. So now sum of the forces acting on the first object in the x direction equals m1 a1 x. Okay, so carefully, all the forces. I will start with the positive. Tension, fully in the positive x direction. It goes into the equation with plus. T. Then, this is perpendicular, nothing. So the component of this force, F cosine theta in a positive x direction. You see this blue, green vector. In the positive x direction, so plus F cosine plus F times cosine theta. Then what else? Okay, let me write this force. Component of the gravitational force, this negative x direction, so minus mg sine minus mg sine theta. And what else? And kinetic friction. You see this kinetic friction force in the negative x direction, minus Fk equals to mass. Okay, I will drop all these subscripts next to the acceleration because we're going to have acceleration, and magnitude of this value of the acceleration is the same for this object and that object because the system is coupled, connected rigidly, almost like through the stretched cord. So I'm going to drop that subscript. And m1 times a. Whew. I think I didn't lose any forces. And so now our kinetic friction should come from the above into this equation. And that's why I started with the y direction. All right. Okay, so now let me rewrite it all. So it will be lots of terms. T plus F cosine theta minus mg sine theta. I'm just rewrote these three terms, and now instead of that force, it will be minus mu k mg cosine theta plus F sine theta equals to m1 times acceleration. Lots of rewriting. That's the only complication. How many unknowns do we have in this equation? Just one? Big greedy. Definitely acceleration. That's what we need to find. Do we know tension? Yeah, two unknowns. Two unknowns, one equation, not enough. So, but we have a second box, hanging and waiting, right? So that will give us the second equation, and as a result, we'll have two equations with two unknowns which can be solved. So this is the equation number one, and now M2, the second box. So you see, for M1, we apply equation in the y direction, x direction. Here, only one equation. Sum of the forces acting on the second object in the y direction equals M2 A2y. But we know because of the object, because these objects are connected, this is the same acceleration as that one in absolute value. Right? And another thing, guys, look. I assume that my system is kind of moving that way and also accelerating that way. As a result, you see, when I applied this acceleration, I wrote as positive in the positive x direction. And so this object accelerates downward, and it's in the positive y direction. So in the equation, it will be also positive. Right? So now, it's easier. M2 G minus tension equals to M2A. Okay, so that's the equation number 2. And since the second equation is, two unknowns, two equations, physics is over at this point, right? So now we just need to solve for acceleration. So now let me write two equations plus two unknowns. So the rest is algebra. Physics, we applied all the physical ideas. Okay, let me check to make sure that my equations are correct. M2G minus T. Yeah. Okay, so of course you can get tension from the second equation, plug it in the first equation. But I would do this. Can I, for example, take equation number 1 and add it to the equation number 2? It's a legitimate mathematical operation, which, and if you do this, look, here tension is positive, here tension is negative. If you add these two equations, tension will be cancelled, and you will get just one equation with one unknown. Yeah. M2, why would it be 0? No. We're not pushing. Actually, one of the main driving forces is this M2G, right? This gravitational force. With the help of this force, that's what drives the system forward. Crazy, right? You see that? So this acceleration cannot be negative. This acceleration of this object and acceleration of that object must be the same in absolute value, of course, in absolute value, in magnitude. Okay, so now let me add equation number 1 and equation number 2 to get rid of tension. To get rid of T. Okay? But of course, if you extract tension from here, plug it in the first equation, it will be the same. So if we do that, I will get then this will be M2G over here, M2G plus F cosine theta. Just left-hand side I'm adding and right-hand side I'm adding. And of course, they must be equal. So now this over here plus F cosine theta minus m You remember what you told us? We need to distinguish masses, right? So, and I was very sloppy. This is M1. This is M1, and now I'm because there are so many terms, I was focusing on looking at the forces. So this is M1, and this is M1. Yeah, only in this. Over here also. This is M1, M1. Anything else? No, this is M2, M2. Yeah, in those two terms. And over here, it's M1. And over here, M1. Okay, so now this is M1 G sine theta minus mu k M1 G cosine theta plus F sine theta equals to. Okay, so that's the left-hand side. Left-hand side. On the right-hand side, add this and that, so it will be M1A plus M2A. So I can write M1 plus M2 times A. Ugly equation, right? So now, and one unknown. So pretty much now we just need to move this M1 plus M2 downstairs, and that will be the answer. So acceleration will be equal to, how can I combine them? I can factor out M1G over here, and yeah, maybe I will do this. M2G, combine this term with that term, and these guys with that guy. So I can factor out F and M1G. So it will be plus F cosine theta minus mu k sine theta. So I combine this and that. And now these two guys. So it will be minus M1G sine theta plus mu k cosine theta. Yeah, that's it. Makes expression smaller and divided by the total mass. So we just added one force. As a result, we have much larger number of terms in the expression. Of course, it's not very likely that I will give a problem of this. No, just a second, I see your hand. Exactly, it's very similar. I just wanted to play with the additional force so that we need to decompose it, find this component, that component, right? Because for the exam, maybe this problem is a little bit too much. But I just wanted to play with some additional force acting on the system, right? How to decompose, how to include it, right? So, yeah. T, what did I do? You see what I wrote? I added this equation and that equation. Added left-hand side of the equation, this plus this, and this plus that. It's legitimate. Okay, what essentially I'm doing, I skip one step. So you can do this. You can extract T from here. T will be equal M2G plus M2A, and plug it over here. But I kind of skipping half a step or one step. I just add equation 1 to equation number 2 because this tension is positive, here tension is negative, immediately it disappears. Just some mathematical tricks which can be easily applied. So now if you want to get tension, take acceleration, plug it there, get tension, but I'm not going to do it because it's really getting messy, right? Really messy. Yeah.
So for the subscript for the first M on G, the 1 plus 2 is equal to the
This is 2. This is 2. This is 2. Let me make it bigger. M2. Again, the goal is how to show how to handle additional force on the incline acting on the object. The whole problem, it will be too much a little bit for the exam. For 50 minutes exam. If it was a final exam, yeah, I would think about it. Okay, so then next problem, it's without this force. You can look at by yourself as a practice exam, as a practice problem. All right, so now let me just quickly look at Atwood machine without getting through everything. I just want to draw a free body diagram and write down the equations, Newton's second law. But I don't want to solve the whole problem because we still need to discuss rotational dynamics. Okay, can I start erasing? Okay. Okay, good. Let me start from the top, so it will be number 5. And when you solve it by yourself on a piece of paper, it sounds like it's not a big deal. But when you start discussing it in the class, right, so you realize that maybe too much for the exam. This problem or that problem. It's quite often when you prepare for the recitation classes, you think, we can solve this and then this and this. So it's very simple, very easy. But when you start discussing, when you start actually solving, you realize that actually it requires much more time than you thought. So, number 5. So, Atwood machine. I think we discussed that in one of our lectures. I think I did it in the lecture. I just want to, as I said, draw a free body diagram and write down Newton's second law. I don't want to solve it for something. So essentially, it's a pulley, massless, frictionless. No mass, no friction. Atwood machine. It's a classic system, mechanical system. And so there are 2 objects. One is hanging on this side. One is hanging on that side. So this is M1, this is M2. Right. So usually masses are given, M1, M2, and usually the question, find acceleration or maybe tension, something like this. But again, I don't want to solve the problem completely. Again, if you don't know even how to solve the problem, just follow the procedure. Coordinate system, all the forces, and then apply Newton's second law. Again, you can make mistakes here and there. Maybe you can skip terms. But the problem, maybe 70% of the problem will be definitely covered. So forces. M1G, then tension force up, right? Acting on the chord. Acting on the object along the chord away from the object. This is M2G, and Since the chord is massless, it doesn't matter which point on the chord you take, tension is going to be the same. This point, this point, this point, over there, over here, tension, absolute value is going to be the same. It's a consequence of the fact that chord is massless. So, as a result, no subscript next to the tension over here and there. Tension is the same. Magnitude of the tension the same. And so now, coordinate system in this case, of course, only one coordinate, y-axis, for example, but upward or downward, you cannot win. Every time one of the accelerations are going to be negative. And in this case, since numbers are not given, masses are not given. So let's assume that, for example, the system accelerates this way, or maybe that way, right? So we can make that assumption, and if at the end acceleration is going to be positive, so your assumption was correct. If acceleration is going to be negative, your assumption was wrong. So what a big deal, right? So now let's assume acceleration is this way. And now let me introduce coordinate system. Which way I picked in my notes? I picked it this way. Downward. And now the same y-axis is going to work for both masses. Again, you can introduce two different, but I don't think it's going to make your life any easier. Okay, so now everything is here. So now we can start applying Newton's second law. So let's start with the first one. And as a result, the first equation will be positive direction downwards. So this is positive, m1g. Tension is negative, equals to mass time. And acceleration is positive, right? Relative to this chosen direction, that acceleration is going to be positive. And again, acceleration, absolute value of acceleration of this object and absolute value of acceleration of that, the same. Because again, essentially they're sort of rigidly connected through a stretched chord. Their velocities are going to be, the speeds are going to be the same. Acceleration is the same in absolute value. So it's equation number one. So now the second, sum of the forces acting on the second object. So it will be what now? Still the same, m2 g is positive and this is negative, right? So it will be m2g minus t equals to m2. And what about acceleration of the second object? This acceleration, we assume it's a downward. So this acceleration was positive, and this acceleration is negative. Be careful, guys, because it's a very common place for mistakes when students try to write down Newton's second law for the Atwood machine. Every time one object is going to have positive acceleration, and then the other one must have a negative acceleration, right, all the time. So it will be m2 times minus a. It's product. So that is the equation number two. Again, if we assume acceleration this way, relative to this coordinate system, this acceleration downward positive, this acceleration you see upward negative. And that's one of the main reasons why I wanted to discuss Atwood machine, to emphasize on this, that one of the accelerations positive, the other one must be negative all the time. You cannot win, right? Otherwise, I would skip Atwood machine. See that, everyone? Okay, good. And so from now, you can solve for acceleration or tension. For example, if I wanted to, for example, get rid of this tension, I would just take equation number 2 and subtract it from the equation number 1. That tension would be negative, this tension would be then positive, and of course you will get only an equation for the one unknown a. But again, I don't want to do that. My goal was just want to write down these equations. So two unknowns, tension and acceleration, two equations. You can solve it for whatever you need to solve. Right? So two unknowns, tension and acceleration, and two equations. So physics is over. So the rest is algebra. Right. Okay. Again, the goal was to emphasize on that. And again, practice free body diagram. Okay, so then more systems to skip with two bodies. Okay, 2 hours. So another 30 minutes, and I think we should be able to finish it. So what's left? What's left? This rotational dynamics. So let's solve a couple of problems about rotational dynamics, and then we'll call it a day. Okay, questions about this Atwood machine. We solved this Atwood machine problem in so many different ways. I think maybe 5 or 6 different ways. First Newtonian formalism, then energy approach, then Lagrangian approach, Hamiltonian approach, Hamilton-Jacobi theory. I solved so many, this problem using so many different methods. Right, okay. So now next one is what? Some object on a string, and we're going to spin it in a vertical direction. I mean, not in the vertical plane, in the vertical plane. So number 6. So ball on a string. Okay, let me draw the picture first, and then I will write down what is given. I even at some point search on YouTube how to draw a circle on the whiteboard. And actually, I even read some techniques, so you need to make sure that your shoulder is in front of the center of the of your circle, and you naturally create a circular motion with your hand, but still it doesn't work. So radius is given. What r? So r equals to what? 1 meter. Then mass of the ball is 1 kilograms. And okay, so at the top, in part A, we're going to discuss a top point. Top point, so the ball is over here. Here's the string or the cord. Let's assume it's spinning this way, counterclockwise, and the velocity at the top is given. I think it's given, right? So let me check. Yeah, 10 meters per second. V at the top. So that velocity equals 10 meters per second. Yeah. So we need to find the tension in the cord. Find T at that top point. We solved something similar in the recitation class. I just want to refresh it and then solve another problem of a similar type. Still, Newton's second law must be applied. But now we need to choose the most convenient coordinate system. Again, draw a free body diagram and apply Newton's second law in the radial direction. So you remember, so about the coordinate system, you imagined sort of freeze this system, right, at this point, and introduce these coordinates. Tangential direction, t, and radial direction towards the center. Instead of x and y, we use r and t. Right? So then, at this point, so what's next? We can start identifying all the forces. Right? Gravitational force, straight down. So mg. And then, what else acts on the body? What else acts on the body? On the ball? Oh, no. There is no such thing as a rotational force. You see, only these forces we identify. Tension, normal force, friction, gravity, gravitational force, and any of those forces can play the role of the centripetal force. Or maybe superposition of several forces can play the role of the centripetal force. There will be centripetal force here, and that's what I'm trying to identify. So first, gravitational force acts on the ball because there's the earth underneath. So what else acts on the ball? Normal force, again, it only appears if there is an interaction between your object and this surface. Surface is below me, right? So right now I'm experiencing normal force. What do we have here? So ball. So it interacts with the earth. What else it interacts with? Of course, the string. So which force string exerts? Of course, tension. Right, of course, tension. Right, so guys, be careful, because I know it, and that's why I started asking. It's very common when our students sort of confuse normal force and tension force. Right? Very common, very, very common. Right? So if there is a cord, rope, string, there must be a tension force, right? Okay, and along the cord, away from the object. So in this case, straight down as well. So this will be, which way I label it? T? Yeah. I label it as T. So now that force which you try to call rotational force, although there's no such thing, in this case we usually call it like centripetal force. It's a superposition of these two forces, mg and t. Mg plus t plays the role of the centripetal force. Now two actors play one role, right? Okay, so now, and of course, we can say also these two forces provide the centripetal acceleration. So now let's apply Newton's second law in the radial direction. So at the top, sum of the forces in the radial direction equals to mass times centripetal acceleration. Again, the same, ubiquitous Newton's second law. And again, you remember, this is our positive direction, downward r. So this force is positive. This force is positive as well. So both of them positive. So I can write T plus mg. And centripetal acceleration, again, we did not derive it in the lecture. Don't feel like doing this, right, in this course. So equals to mass times centripetal acceleration, v. Okay, it's a top squared over, I use r capital. Okay, why not? Radius of the circle, circular trajectory. Yeah, this is top tension at the top point, because tension will vary depending on the point, right? So, and this is the only correct at that particular top point. Okay, so this is our unknown. Mass is given, radius is given, speed is given, so everything is given. So we just need to solve it for the tension at the top. So T at the top equals to mg plus mv squared over r. On purpose, first I wrote mg because it's the weight. And then on top of weight, we have some, Oi, do. You didn't see this. You didn't see this. I will have to erase it from the video. Cut it. Okay, so mg goes to that side with minus mv. I'm also getting tired a little bit. All right, so minus mg. So now it's correct. So this is positive, and this term goes to that side, of course, with minus side. Okay, so if you plug numbers, so you will end up with 90.2 newtons. Okay, you can round it to 90 newtons. Again, on the exam, I'm not very picky in terms of significant figures. Right? So again, don't use 10 sig figs where when the numbers only with 2 or 3 sig figs are given. It's just reasonable. Okay. Again, these problems are even easier. So now part B. What is in part B? So let's assume that we know the maximum tension that this cord can handle. It's given like almost 110 newtons. So we need to calculate what's the maximum speed. What is allowed maximum speed of the ball at the bottom point to prevent breaking the cord. So we need to calculate the maximum speed that we can use to keep the cord as one piece. All right, so now at the bottom. Right, so we need to calculate V maximum if we know that T maximum is 109.8 newtons. So the cord can stand only this tension. This is the maximum tension which it can stand. And why was the bottom point picked? Because over there the tension usually is the largest. If you recall the problem which we solved in the recitation class, the tension, the smallest, when the point is at the top, the ball is at the top. I see your hand. And maximum when the ball is at the bottom. Yeah. No, this is 1. Right. So this is my 1. Just vertical line and then the trunk or the what. So essentially, again, we just need to apply Newton's second law. First, identify forces. So this is the ball. It moves with this velocity, which we need to find V max at the bottom. Of course, the cord or the string. Right. And now forces. Gravitational force still straight down. I've seen in the past occasionally students still flip gravitational force, but it's obviously wrong. So mg. Now tension, again, along the cord, away from the object. Away from the object is upward. Tension is upward now. So here tension was in the same direction as gravitational force. Now they're in opposite directions. Right? And in coordinate system, again, imagine freeze the system at this moment and introduce coordinate system. Tension and, I mean, not the tension. Yeah, I'm getting tired also. Tangential direction, t-axis and r-axis towards the center. So tension is positive, mg is negative relative to the chosen positive direction. So now let's apply Newton's second law again. So it will be positive. t at the bottom, minus mg equals to mass times velocity at the bottom squared divided by r. So right now I wrote this equation in general. You see, I didn't add subscript maximum, right? And now I'm going to look at that extreme case when we apply the maximum speed and we know this maximum. So now this is in general. In general, for any v. And now let's apply for the critical case. And now apply it for a critical case. So that maximum. Right. Okay, so T max minus mg equals to m v max squared divided by radius. What we need to find? Velocity. Velocity needs to be found, right? So v max squared will be equal to r over m t max minus mg, yeah. Okay, so now I will erase this 2 and put a square root sign. Right? Yeah, of course. So radius is given, mass is given, a maximum tension is given, mass g is given. So you can plug numbers and you will end up with 10 meters per second. Based on my experience, usually students do better with this rotational dynamics. It's less lengthy than. You know what? Let me just quickly discuss conceptually just the forces, and we'll call it a day. What if? Okay, let me put a bullet. What if we have, for example, a circular road? And car, is passing the top. And let's say we want to find, okay, let's say just apply Newton's second law. So essentially, this is the circular trajectory, right? Radius is given, right? So we need to introduce coordinate system. So this is tangential direction. This is radial direction, right? And now let's draw all the forces. Gravitational force, straight down. Then what else acts on the car? Normal force, and that, of course, up. Yeah, guys. Normal force is up, right? Because the surface is below, so normal force. And now if you apply Newton's second law in this case, so it will be mv squared over r equals to mg minus t, right? And the problem can be find, I know, maybe velocity, or find tension, or maybe radius. It depends on the situation, but every time you'll have to do these steps. Now, what if I look at this case? What if road is like a valley? So now the car is at the bottom of this hill. So velocity. This is radial direction towards the center. This is tangential direction. Now forces, gravity is still down. And now normal force is still up. Normal force. And now if we apply Newton's second law, so it will be mv squared over r equals to, now normal force is positive, right? Because r direction is up. And gravity is negative. Over here, gravity was positive, normal force was negative, but now everything is reversed, right? You see the difference. Be careful, because if you made that mistake, of course. Mg. Yes, of course. Sorry. Of course, it's a normal force. Yeah, thank you. It's still from the previous problem. So normal is positive, and minus the weight. Yeah. And again, a problem can be about finding the normal force or finding velocity or the radius, all possible situations. Everything is possible. Now let me give you a couple of other examples of this type. So let me separate this. So now what if you remember that the loop show or demonstration? So let's say loop the loop. We discussed it in the lecture, but I just want to compare all the examples. So in the loop situation, we have circle, and now car or whatever object is on the surface but upside down, right? So if you provide enough velocity, the object can move, can experience circular motion, but of course you need to provide large enough velocity. So now let's do the same. Let's just write down Newton's second law. Let's assume it's moving, I don't know, this way, so velocity. Again, coordinate system, T, R. Now, forces. Gravitational force, still straight down. We cannot change that. We're not gods yet. So, mg. Normal force. What's the direction of normal force? Think. You think that, what do you think? No, definitely there should be normal force. Upward or downward? Down? Okay, guys, so you see now the car is upside down. The surface is above the car. Essentially, it's this case. You see I drew over here. So the person, if the person touches the ceiling, and essentially that is now a ceiling for the car, right? So of course the surface exerts force perpendicular, and now it will be down because the surface is above you. So over here the surface was below the car, so the normal force was up, but now that's the physical situation, and the surface is above, so the normal force will be down. So be careful with that, right? So because their car was riding over the hill, now it's a it's sort of like a riding under the hill. Driving under the hill. So what? Normal force. Normal force. Right. And now if you apply Newton's second law over here, so it will be mv squared over r equals to, are both positive. Both forces are positive, mg and normal force. So mg plus n. And again, you can solve it for whatever needs to be found. Again, it depends on the situation. Sometimes force, sometimes radius. I mean sometimes velocity, sometimes radius, sometimes normal force. Right. Then, so it's in this case. Now let's look also at the bottom. And that will be the last example. So the car driving this way. This way. Still, radial direction now is up. every time you change the direction of r, right, towards the center to make centripetal acceleration positive. And so forces, gravity down, I don't have space for the gravitational force, mg, and the normal force now is up because surface is below. Now every time see where the surface is, right? So now normal force is up, right? Okay, and now if we apply Newton's second law for this point, mv squared over r equals to normal positive, weight is negative mg. So again, don't try to write this equation without drawing coordinate system. I mean, without drawing the free body diagram, because even I wouldn't trust myself. Right? Just quickly sketch the picture, right? And by looking at the picture, you can write down the equation. Okay, so I think it should be enough. Of course, I prepared more problems, but you can look at them by yourself. I will scan everything as usual, upload on Blackboard, and you can practice that. So again, the exam is on Wednesday. If you have any questions, we still have plenty of time to discuss. And as I sent you email, problems about universal law of gravity is not going to be on the exam, right? Because in my recitation classes, I haven't covered them. Plus, you haven't finished your homework about that, so it doesn't make sense to include those into the exam. Okay, if you have any questions, I'm here. And see you on Monday.